Great, thank you. So thank you for having me. So I'm going to present this joint work on unpaired kidney exchange. So let me start right away. So what is kidney exchange? Basically, it's a problem where you have pairs of incompatible patients and donors who are willing to exchange their donor to find a compatible living donor. And so to do so, you have different technologies that exist today. So what are the two main technologies that are used today? The first one is just pairwise exchanges that you can see on the left. So you have two pairs of incompatible patient and donors who are basically cross-compatible, and they would just exchange their donors. Okay, and so the advantage of this this technology is that you make the exchanges simultaneous. So then a donor gives while the patient receives. So you have no renege risk of donors. So donors cannot say no to this donation because it's done simultaneously. It's widely used in the world, in the UK, in the US, or in France, for instance. But the drawback is that it's limited on size. So such cycles of exchange are usually performed up to 3 or 4 pairs in the exchange. And you have this famous problem in economics, which is the double coincidence of words. So to make this exchange possible, you need that your donor is compatible with the patient of the other pair, but also the donor of the other pair is compatible with you. Okay. And so the second main technology that exists today is called chains. So what is a chain? You start with a donor without any associated patient. Usually it's an altruistic donor, or in other countries, it can be a deceased donor. This donor would start to give to a patient in the pool of pairs. And then we will ask the donor of such patient to whether he or she wants to give, and then we'll give to another patient of another pair, and so on and so forth. And so the advantage of this is that the exchanges are sequential now over time. Then it makes a relaxation of this double coincidence of words, because now a donor can give before the associated patients receive. Okay? And so you have no limit on the length of this chain of exchanges. It's also widely used, for instance, in the UK or in the US, but not in France, for instance. And now you have a new risk that appears because the donor gives after the patient receives, is that you might have a risk that the donor says no in the future. And so there is a renege risk for donors. And so what we introduce in this paper to relax this problem of double coincidence of words is to go even further than chains and basically to allow also donors to give before their patient receives. So in the literature, what has been shown is that chains perform much better than pairwise exchange, both in terms of number of grafts or waiting time of patients. So our proposal is now, in addition to having donors to give after their patient receives, you have donor who gives before their patient receives. And so basically you realize transplantations as soon as they are possible. So if you have a new pair coming in the system, let's say the one on the right, then if the donor is compatible with the patient in the pool, you make the transplantation immediately. And then you will have the two possible situations. First, the patient of the pair which arrived as a patient waiting without his donor because the donor gave before. And so you have a waiting list of these alone patients that we call P that are waiting in the system. Then also you have the donor of the second pairs, the patient received the kidney. So he's also waiting without his patient now in the system. And this is the waiting list T. And by continuing this exchange over time, then this is the mechanism we propose. And so now you have two possible issues in this mechanism. The first one is that as before for chains, because donor gives before their patient receives, you might have a renege risk of donors. But also now that the donor gives after the patient receives, you might have an issue of waiting time of these alone patients in the system, the patients who are waiting in P. Okay, and this proposal is basically a generalization of what is called the Advanced Donation Program of the NKR kidney exchange program in the US. Okay, and so what we do in this paper, we introduce this unpaired matching algorithm. We keep in mind these two issues that I just mentioned, and we have two parts in the paper: a theory part with a simple dynamic model, where we show that basically the waiting time of patients in the system in unpaired is very close to an optimal mechanism that we define. And it performs much better than the chain and much better than pairwise exchanges. And then we have an empirical part where, using data from French kidney exchange, we perform counterfactual analysis. And we show that the two issues that I mentioned are strongly weakened in a large market simulation. So we use French data or also replicate pools in the US, such as APD and NKR. And we also propose a modification of the algorithm with the help of deceased donors to solve the two issues for small markets in terms of waiting time. So let me go straight into the theory now. So the model is very simple. Time is continuous, and pairs arrive over time with the Poisson process. Then you have two types of pairs. The first one is when patients are hard to match, meaning that they are compatible with a random donor with probability pH, independently of donors. Okay. The second type of patients are easy to match patients. And for the sake of the talk, let me assume that P is equal to 1. So this is their probability to be compatible with a random donor in the pool. Okay. And so in the paper, it's relaxed, obviously. And then we assume that there is no exogenous exist in this model, and basically the pairs of patients donors stay in the system until they are matched. Okay. And so why do we model this in terms of two types of patients? It's because it's very much what we observe in many pools across the world. So this is the data from France. So if you calculate the probability for a patient to be compatible with a random donor, with blood type compatible with this patient, you find two types of patients. Patients who have a probability to be incompatible very close to 0. So this is what we call the easy to match patients. And patients who are very hard to match and are almost never compatible with a random donor. And so in terms of objective, we focus on the average waiting time at steady state of a given algorithm. And so the expected waiting time of a patient in the system is the combination of the waiting time of hard to match patients and the waiting time of easy to match patients. So the first simple thing that we show is that for the algorithm that we study in the paper, the waiting time of easy to match patients times the probability of hard to match patients tends to 0 when pH tends to 0. So all of our results will hold when we let the probability to be compatible for hard to match tends to 0. Okay? And so we don't need to study the limit of the easy to match patients. And so we have to focus on the limit of the waiting time of hard to match patients. And so we study three different types of algorithm. The first one is the pairwise exchange. So as soon as a pair enters the system, if there is a cross compatibility with the pairs we are currently waiting, you realize the exchange and you break ties arbitrarily. The second mechanism is the chain. So we assume that there is one altruistic donor at the beginning of the time. And as soon as this donor is compatible with an arriving patient, you try to implement in the pool a maximal chain by randomly searching for the next patients to give in that chain. At the end of this maximal chain, you have a donor who left in the system, and you use this donor to be the new altruistic donor in future periods. And you see this such mechanism over time. Okay? And our proposal of unpaired algorithm is basically you match patients upon arrival if there is a compatible donor, and you match the donors upon arrival if there is a compatible patients. Okay? And so you can study the evolution of the three algorithms. And basically, the summary of our theoretical results are given in this graph. So this is the value of the limit of the waiting time of hard to match patients times pH when pH tends to 0. And we can show the value of this limit for different value of lambda, and lambda is basically the proportion of hard to match in the system. So what our theoretical results say is that the unpaired algorithm, which is the yellow line at the bottom, is very close to an optimal mechanism, which is the lower bound that you can achieve in this system. It performs better than chains, which is the red line in the graph, and much better than pairwise, which is the green line. So let me break through these different lines to explain to you the intuition. So first, you can show that no algorithm can do better in terms of waiting time than a order 1 over pH for hard to match. And so this is this blue line here. And the intuition is that as a patient, once you arrive, if you are not matched immediately, then you need to wait for a next compatible arrival in the future. And in expectations, it takes for you 1 over pH periods for hard to match patients. And this is basically why you cannot do better than an order 1 over pH. That's the heuristic. Okay. So then in terms of for the pairwise algorithm, it has been shown by Ashlagi and al. So you have two regimes. One regime where you have more easy to match patients than hard to match patients, so lambda less than 1/2, and basically they characterize the constant. And the intuition is that once you have more easy to match patients, you can use them to help hard to match patients to be cross-compatible. So in that case, the waiting time of pairwise is of order 1 over pH, which is basically this left side yellow line. But when you have more hard to match patients than easy to match, then you have an accumulation of hard to match patients in the system. And these hard to match now need to be cross-compatible among themselves. And this happens with probability pH squared. And basically, the expected waiting time for these patients is of order 1 over pH squared, which basically explodes in this graph since we multiply by only pH. Okay? And so an important observation is that this upward slope of this curve here. And so it says that the more easy to match patients in the system, the better for hard to match patients. And basically, they help hard to match patients to be cross-compatible. And that's the intuition of why you have an upward slope. So then for chains, again, Ashley and Al have characterized the constant of the waiting time. And basically, since you don't do cross-compatibility anymore, then the waiting time is of order 1 over pH for hard to match patients. And you have two observations. The first one is you still have this upward slope where the more easy to match patients, the better for hard to match patients. And the intuition is that the more easy to match, the more they help to start a new segment of the chain, because the chain starts again as soon as a new patient is compatible with the alone donor. And an important observation is that the more hard to match patient in the system you have, the more the waiting time of hard to match explodes, and basically it explodes where lambda tends to 1. And the intuition is that when you have only hard to match patients in the system, the probability to start a new segment of the chain vanishes. And so that's why the waiting time of hard to match explodes. And so our main result is the characterization of the waiting time of Unpaired, the algorithm we propose. And basically, we show that it improves both upon pairwise and chain. So the ratio of waiting time for pairwise and unpaired is of order 1 over pH. And we can also show that the ratio of hard to match patients of unpaired over chain is greater than 1. And basically, there are two important observations, is that unpaired algorithm does not need easy to match patients to match hard to match patients anymore. And so you have two consequences. The first one is that this slope is downward now compared to pairwise and chains, which means that the more easy to match patient in the system, the worse it is for hard to match. Because in unpaired, they just take away donors from hard to match patients, which is an important difference compared to chains and pairwise. And the second observation is that the waiting time of hard to match does not explode when lambda tends to 1. So compared to chain, there is no, when you have only hard to match patients in the system, the waiting time of hard to match does not explode. So which is also an important difference with the chain algorithm. And so the last result that we have is that due to the lower bound that I gave you before, we can show that the unpaired cannot do worse than 2 times the waiting time of any algorithm. And so basically the ratio between the lower bound and unpaired is basically lower than 2. And so, which means that it's very close to any optimal algorithm that you might define that will be very close to the lower bound. And so these are basically our theoretical results, which says that unpaired is very close to any optimally defined algorithm, which performs better than chain and then better than pairwise. Okay? And it's very surprising because unpaired is a very simple online greedy algorithm. There is no optimization going on for forecasting the future and so on and so forth. Okay. So let me move to the empirics now to show you the counterfactual simulations. So we use data from France. And so France has been using only pairwise exchanges since December 2013. And so we have data from this date to February 2018. And it's basically a very small market because on this period, only 78 pairs participated to this kidney exchange program. And so we have also data on 540 pairs who participated in, who choose to do a desensitization, meaning that a medical procedure that allows them to be compatible with their incompatible donor. Okay? And so we draw randomly arrival times consistent with participation, and we assume that pairs do not exit exogenously. So on these 78 pairs, these are the results. If you use pairwise, you only match 22 of them, and the average waiting times is basically 700 days. If you try to introduce a chain in addition, then you have a number of graphs that increase to 23, and the waiting time decrease a little bit. If you try to use unpaired, then you graft 44 of these patients, and the waiting time decreases to 400 days. And if you try to find the best possible match ex post that you could have done to minimize the waiting time, which we call omniscient, you basically match only 45 patients, and it's very close to the unpaired in terms of waiting time, which is consistent with our theoretical results. But the problem is that if you see the waiting time of alone patients in the system, the waiting list P, it's still very high. Okay, so the issue that I mentioned at the beginning, it's still present here. And so how to reduce the waiting times of this patient in P? You might have two solutions to do it. Maybe it's just a small market issue. So we simulate large markets in France and also using data from the US, simulated pools from the US, APKD and NKR. And we also propose a modification of the algorithm when we use offers from deceased donors to reduce the waiting times of these patients in P. And we simulate this using all data on the French deceased donor list that we have available. Okay. And so basically the intuition that strongly weakens this issue of waiting time of patients in P. So let me give you the large market simulation. The first one is that we include all the pairs we did desensitization in the kidney exchange program in France. And the second set is the simulation of US pools of APKD and NKR. And so these are the results. So if you see basically NKR, which is the biggest program of the three, the match rate is very close to omniscient for Unpaired and significantly better than Pairwise. And in terms of waiting time of patients in P, you see that it strongly decreases. And so it weakens in large market, this waiting time of patients decreases. And if you try to use deceased donors offers for patients in P in the small pool of the French kidney exchange program, you basically also find that it strongly decreases the waiting times of this patient by increasing also the number of overall grafts. So this is the data set on the 78 pairs in France. And so you can see the waiting times in P is only 77 days. And the median is also at 4 days, which is very low. And so again, we have a modification for smaller markets that might also help to solve this issue of waiting times for alone patients. And so this is it. So let me conclude. So in this paper, we have a theoretical model that shows that our proposal of unpaired kidney exchange is very close to optimal and performs better than chain and pairwise. And basically, empirically, we show that the theoretical results are confirmed. And the two issues that we mentioned are weakened in large market and also can be solved in smaller markets by using the offers from the deceased donors.